Hello friends, good evening. Today I plan to read out an article from the Quanta magazine on artificial intelligence. To teach computers math, researchers merge AI approaches. Large language models still struggle with basic reasoning tasks. Two new papers that apply machine learning to math provided a blueprint for how that could change. So this is quite an old article dated 15 February 2023 by Kevin Harnett. The world has learned two things in the past few months about these language models, large language models, the computational engines that power programs such as ChatGPT and DALL-E. The first is that these models appear to have intelligence and creativity of a human. They offer detailed and lucid responses to written questions or generate beguiling images from just a few words of text. We all know about ChatGPT, right, today. The second thing is that they are untrustworthy. They sometimes make illogical statements or confidently promote falsehood as fact. They will talk about unicorns, but then they forget that they have one horn, or they will tell you a story, then change details throughout, said Jason Root of IBM Research. There are more than just bugs. These are more than just bugs. They demonstrate that LLMs struggle to recognize their mistakes, which limit their performance. This problem is not inherent in artificial intelligence systems. Machine learning models based on a technique called reinforcement learning allow computers to learn from their mistakes, to become prodigies at games like chess and Go. While these models are typically more limited in their ability, they represent a kind of learning that LLMs still haven't mastered. Reinforcement learning is improving the AI framework from the feedback. We don't want to create a language model that just talks like a human, said Yuhai Tony Yu of Google. AI, we want it to understand what it is talking about. So understand and reasoning, those are the concepts that we are trying to implement in computer. Wu is a co-author on two recent papers that suggest a way to achieve that. At first glance, they are about a very specific application, training AI systems to do math. The first paper describes teaching an LLM to translate only math statements into formal code that a computer can run and check. The second trained an LLM not to just understand natural language math problems, but to actually solve them using a system called Minerva. Together, the paper suggests the shape of future AI design where LLMs can learn to reason via mathematical thinking. We have things like deep learning, reinforcement learning, AlphaGo, and other new language models, said Siddharth Gadgil, a mathematician at the Indian Institute of Science in Bangalore who works with AI math systems. The technology is growing in many different directions and they all can work together. Not so simple translations. For decades, mathematicians have been translating proofs into computer code, a process called formalization. The appeal is straightforward. If you write a proof as a code, the computer runs the code without errors, you know the proof is correct. But formalizing a single proof can take hundreds or thousands of hours. So this is a picture of Tony Yu. He recently co-authored two papers that taught large language models to translate and solve math problems written in natural language. Over the last 5 years, AI researchers have started to teach LLMs to automatically formalize or auto-formalize mathematical statements into the formal language of computer code. LLMs already translate one natural language to another, such as from French to English, but translating from math to code is harder a challenge. There are far fewer example translations with which to train an LLM. For example, the formal language don't always contain all the vocabulary necessary. When you translate the word cheese from English to French, there is a French word for cheese, Root said. The problem is in mathematics, there isn't even the right concept in the formal language. That is why the 7 authors of the first paper, with a mix of academic and industry affiliations, chose to auto-formalize short mathematical statements rather than entire proofs. The researchers work primarily with an LLM called Codex, which is based on GPT-3, a predecessor of ChatGPT, but has additional trainings on technical material from the resources like GitHub. To get Codex to understand math well enough to auto-formalize, they provided it just 2 examples of natural language math problem from their code translations. After a brief tutorial, they fed Codex the natural language statement of nearly 4,000 math problems from high school competitions. Its performance at first might seem underwhelming. Codex translated them into language of mathematics program called Isabelle with an accuracy rate of just under 30%. When it failed, it makes up terms to fill up gaps in translation lexicon. A team of researchers taught Codex, a type of text-driven AI program known as large language model, to translate natural language mathematical statements into formal code that can be read by mathematics program. Prove that there is no function f from the set of non-negative integers into itself such that f of fn equal to n plus 1987 for every n. So this is representation of the same problem into computer code. I am not going to read it. Sometimes it just doesn't know the word it needs to know, what the Isabelle name for prime number or the Isabelle name for factorial is, and it just makes up, which is the biggest problem with these models. Root said they do a lot of guessing. But for researchers, the important thing was not Codex failed 70% of the time. It was what that it managed to succeed 30% of the time after seeing such a small number of examples. They can do all different tasks with a few demonstrations, said Wendell Lee, a computer scientist at the University of Cambridge and co-author of the work. Lee and his co-authors see results as representative of the kind of latent capacities LLM can acquire with enough general training data. Prior to this research, Codex has never tried to translate between natural language and formal math code, but Codex was familiar with code from its training on GitHub and with natural language mathematics from internet. To build on that base, the researchers only had to show a few examples of what they wanted. Codex could start connecting the dots. In many ways, what is amazing about this is that the authors didn't do much. Root said these models had this natural ability to do this. Researchers saw the same thing happen when they tried to teach LLMs not only to translate math problems but how to solve them. Minerva's Math, the second paper, though independent of the earlier auto-formalization work, has a similar flavor. The team of researchers based on Google's trained an LLM to answer in detail a high school competition level math question such as a line parallel to y equal to 4x plus 6 passes through the point 5, 10. What is the y coordinate of the point when the line crosses the y-axis? The author started with an LLM called PALM that have been trained on the general language content similar to GPT-3. Then they trained it on mathematical material like arxiv.org pages and the other technical material mimicking Codex's origin. They named the augmented model Minerva. Breaking down math, suppose we want computer to prove a square plus b square by 2 is greater than a plus b whole square. It starts with the statements and brings it down to the equivalent logical statement a minus b whole square greater than 0, which is true for two numbers a and b when a not equal to b. So that's the proof. The researchers showed Minerva 4 examples of what they wanted. In this case, that means step-by-step solution to natural language math problems. Then they tested the model on a range of quantitative reasoning questions. Minerva performance varied by the subject. It answered questions correctly a little better than half the time for some topics like algebra and little less half the time for others like geometry. One concern the authors had, a common one in many areas of AI research, was that Minerva answered questions correctly only because it has already seen them or similar one in its training data. The issue is referred to as pollution, and it makes it hard to know whether the model is truly solving problems or merely copying someone else's work. There is so much data in these models that unless you are trying to avoid putting some data in the training set, if it's a standard problem, it's very likely it has seen it, Root said. So this is the picture of Jason Root, a computer scientist at IBM Research, sees potential in large language models but also knows their weakness. They do a lot of guessing, he said. To guard against this possibility, the researchers had Minerva take the 2022 National Math Exam from Poland, which came out after Minerva's training data was set. The system got 65% of the questions right, a decent score for a real student and a particularly good one for an LLM, Dude said. Again, the positive results after so few examples suggested an inherent ability for a well-trained model to take on such tasks. Computer is giving math exams. This is a lesson we keep learning in deep learning, that scale helps surprisingly when with many tasks, says Guy Gur-Ari, a researcher from Google and a co-author of the paper. The researchers also learned ways to boost Minerva's performance. For example, in a technique called majority voting, Minerva solved same problem multiple times, counted its various results, and designated in its final answer as whatever had come up most often, since they have only one answer but so many possible wrong ones. Doing this increased the score on certain problems from 33% to 50%. Also important was Minerva to break its solution into a series of steps, a method called chain of thought prompting. These had the same benefit for Minerva that it does for students. It forced the model to slow down before producing an answer and allowed it to devote more computational time to each part of the task. If you ask a language model to explain step by step, the accuracy goes up immediately, Gatgill said. The bridge problem, while impressive, the Minerva's work came with a substantial caveat, which the authors also noted. Minerva has no way of automatically verifying what it has answered a question, whether it has answered a question correctly. And even if it did answer a question correctly, it can't check the steps it followed to get that were valid. If it sometimes have false positives giving specious reasons for correct answer, Gatgill said. In other words, Minerva can show its work, but it can't check its work which means it needs to rely on human feedback to get better, a slow process that may put a cap on how good it can ever get. I really doubt the approach can scale up to complicated problems, says Christian Szejedy, an AI researcher at Google and co-author of earlier paper. Instead, the researchers behind both the papers hope to begin by teaching machines mathematics using same techniques that had allowed the machines to get good at games. The world is awash in math problems, which could serve as a training fodder for system like Minerva, but it can recognize a good move in math the way AlphaGo knows when it played well at Go. On the one side, if you work with natural language Minerva type of reasoning, there is a lot of data out there, the whole internet of mathematics, but essentially you can't do reinforcement learning without it, Wu said. On the other side, proof assistants provide a grounded environment that have little data to train on. We need some kind of bridge to go from one side to other. Auto-formalization is the bridge. Improvements in auto-formalization could help mathematicians automate aspects of the way they write proofs and verify their work is correct. By combining the advancements of the two paper systems, like Minerva could first auto-formalize natural language math problems, then solve them and check their work using a proof assistant like Isabella HOL. This instant check would provide the feedback necessary for reinforcement learning, allowing these programs to learn from their mistakes. Finally, they would arrive at a provably correct answer with an accompanying set of logical steps, effectively combining the power of LLM and reinforcement learning. AI researchers have even broader goals in mind. They view mathematics as the perfect proving ground for developing AI reasoning skills because it arguably the hardest reasoning task of all. If a machine can learn effectively about mathematics, the thinking goes, it should naturally acquire other skills like ability to write computer code or offer medical diagnosis or maybe even to root out those inconsistent details in a story about unicorns. I'll stop here. Thank you.